In this video, we're going to work on some power series applications, also a little bit of binomial series in here as well. So first question, we want to use series to find the first four terms of the power series for natural log 1 plus x times sine x. We're going to do really a Taylor series centered at x equals 0. So we're doing natural log 1 plus x times sine x. So we have natural log 1 plus x times sine x. And what we wanted was the first four terms. So we want the first four terms. Okay, so what we're going to do here is I'm going to replace natural log 1 plus x and sine x with the respective Taylor series here. So natural log 1 plus x, you can look this up, but this is n equals 0 to infinity. Actually, not 0 to infinity, 1 to infinity for this one. It's negative 1 to the n plus 1, x to the n over n. So that's natural log 1 plus x. Sine x is n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So you could multiply these out or try and get some formula for the coefficient of x to the n here in general, but we only need the first four terms, so I'm going to just write out the first 4 or 5 terms of each of these here. So my natural log 1 plus x, let's see, when n is 1, I get a positive, so I'll get an x, and then it'll be minus an x squared over 2. N is 3, I'll get a, get an x cubed over 3, and then I'll get an x to the 4th over 4, and let's put an x to the 5th over 5. Whoops, I should also do a, sort of ended that as if this ends here. So it should be plus some more stuff here. We might need more there. Probably not here. And then for, let's see, sine x, when n is 0, I'm going to get x here. So I'll get x to the 1st over 1 factorial. When n is 1, I get a negative, and then I'll get an x to the 3rd over 3 factorial is 6. When n is 2, I'll get an x to the 5th over 5 factorial, which is 120, and then there's some more terms here. I already got up to x to the 5th, which matches what I have on the left here, so I've sort of got a nice spread there. I might have to add an x to the 7th term later on. We'll see. And then when I multiply these together, I'm just going to look for what coefficients can I get, or what powers of x. So the lowest power of x is taking x on the left, x on the right. That gives me an x squared. Then I want to think, can I get x cubed? Well, if I take, let's maybe work on the right because there's fewer of these. If I take an x cubed to the 6th, there's no constant term on the left, so I can't get an x cubed. So I have to do x times x squared over 2. That gives me minus x cubed over 2. What about x to the 4th? Well, I could take x times x cubed over 3. That will give me an x to the 4th over 3. Or I could take x cubed over 6 on the right times x. So it'll give me minus x to the 4th over 6. Group those together. What about x to the 5th? I could do an x times a negative x to the 4th over 4. So let's say minus x to the 5th over 5. And I could do negative x cubed over 6 times x squared over 2. That'll give me a plus x to the 5th over 2 times 6 is 12. And I can see already I've got, I mean, there'll be an x to the 6th, x to the 7th, but I've got an x squared, x cubed, x 4th, x to the 5th. That's 4 non-zero terms. I guess you can make an argument. You could end at x cubed and you have a constant term and an x term that are both 0 here, but probably not what's actually wanted here. And then it's just a matter of sort of finding the coefficients for like the x to the 4th term and the x to the 5th term. So x squared minus x cubed over 2. This is 1/3 minus a 6th. That's 2/6 minus a 6th. So it'll be minus x to the 4th over 6. Let's see. This is going to be, let's see, a 1/12 minus a 5th here in terms of the x to the 5th. So that's going to be 5/60ths minus 12/60ths. That'll be a negative 7/60th. So then minus 7 x to the 5th over 60, and then plus some more stuff. But the first 4 terms here, that's really a Taylor polynomial of order 5. Next one. Okay, so that was just finding a power series. Didn't really do an application, really. Now we can start doing applications. So I'm going to do a limit x goes to 0, sine x minus x over x cubed. So what we've got now is a limit x goes to 0, sine x minus x over x cubed. Okay, so if you go back to sort of Calc 1 doing limits, we can do the problem the way we would here. First thing you do is probably plug in the 0. You get 0 minus 0 over 0. That gives you a 0 over 0 undefined. You can use L'Hopital's rule. So we're going to do this here with L'Hopital's rule. What I'm going to do is take a derivative of the top. I get a limit as x goes to 0. Derivative of the top over derivative of the bottom. Derivative of sine x is cosine x. Derivative of x is 1. Derivative of x cubed is 3x squared. So I do that, and then I plug in x equals 0. I get cosine of 0, that's 1 minus 1. That's 0 on top. I'll get 0 on the bottom still. So I got 0 over 0. I can do L'Hopital's rule again. Limit x goes to 0. So derivative of cosine x is negative sine x. Derivative of negative 1 is 0. Derivative of 3x squared is 6x. Plug in x equals 0. I'm going to get 0 over 0 again. So I do L'Hopital's rule again. And what I get is negative cosine x over 6. And then you plug in x equals 0, and you'll get a negative 1 on top, 6 on the bottom. So you can get a negative 1/6 here using L'Hopital's rule. We had to do this 1, 2, I think 3 times here. Now, there's another way using series here. So what I'm going to do instead, let's do it this way, is I'm going to do a limit as x goes to 0, sine x minus x over x cubed. I'm going to replace sine x with its power series. Now, sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus some stuff. And I subtract x and then divide by x cubed. Well, if you look at this, what I have is an x in that sort of Taylor series minus the x. Those are going to cancel out. So that x and that minus x cancel out. And what I'm left with is a limit as x goes to 0 of negative x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial over x cubed. Well, then you can divide the top terms all by x cubed. And this gives us a limit as x goes to 0 of negative 1 over 3 factorial plus x squared over 5 factorial. X to the 5th over x cubed is x squared minus x to the 4th over 7 factorial plus some stuff. Here, well, the 1 over 3 factorial, that's going to be 1 over 6. Actually, it's a negative. I wrote that way it's hard to see. So I get a negative 1/6. Still negative 1/6. The rest of these terms are all going to be 0. So now, since we can get that negative 1/6 this way, looks like I may be writing out a bit more, but if you get used to this, if you look at your series for sine, you say, oh, I take off the x, and then it's x cubed over x cubed. It gives me a negative 1/6. You can almost do this in your head here. So that's really the idea of we can use power series to avoid L'Hopital's rule. Here, really repeat it. Okay, let's look at number 3. We're going to do the same kind of problem. Limit x goes to 0, x times sine x over 1 minus cosine x. So limit as x goes to 0, x times sine x over 1 minus cosine x. So we get a limit as x goes to 0. X, series for sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus some stuff. 1 minus cosine x is 1, not 1 plus, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus some stuff. And then what that gives us, let's see, on top, I'm going to get an x squared minus x to the 4th, 3 factorial is 6, plus x to the 6th, 5 factorial is 120. On the bottom, what I'm going to do is 1 minus 1, those will cancel. I'll get a negative, so I'll get an x squared over 2 And then I'll get a minus x to the 4th over 4 factorial is 24. That 2 is 2 factorial, which is just 2. And then plus minus a negative x to the 6th over 6 factorial is 720. And then there's some more stuff there. Now, oh, and I messed this up. It's not x goes to infinity, it's x goes to 0. If x was going to infinity, it'd be the highest degree terms that would dominate this. But because x is going to 0, it's actually the lowest degree terms here. So it's really the x squareds that are going to sort of dominate. X to the 4th is going to get way, way smaller than x squared here. If that doesn't make sense to you, what you can do, let's maybe do this down below, is just divide everything on the top and bottom by x squared. So you get 1 minus x squared over 6 plus x to the 4th over 120. Dividing the bottom by x squared is 1/2 minus x squared over 24 plus x to the 4th over 720. And then everything except for the 1 and 1/2 are going to go to 0 as x goes to 0. So this is 1 over 1/2, which is 2. So we got a limit of x sine x over 1 minus cosine x going to 2. Next one. Got cosine x minus 1 over e to the x minus x minus 1. So we do a limit as x goes to 0, cosine x minus 1 over e to the x minus x minus 1. Is that right? Yep. Okay, again, I'm going to use power series. This is limit x goes to 0. Cosine x is 1 minus x squared over 2 plus x to the 4th over 4 factorial plus some more stuff. And we're going to subtract 1. And I'm going to divide by e to the x is 1 plus x squared over 2, really factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, plus some stuff. And then we subtract x and subtract 1. So what you get on top, let's see, the 1 minus 1 cancels. You get a negative x squared over 2 plus x to the 4th, 4 factorial is 24. On the bottom, we're going to subtract the 1 and the x. So you have an x squared over 2 plus x cubed over 3 factorial is 6. X to the 4th, 4 factorial is 24, plus some more stuff here. And then it's going to be the lowest degree terms that are going to dominate here because x is going to 0. So you'll get a negative 1/2 over 1/2. This will go to negative 1. Okay, and again, you could do L'Hopital's rule here maybe a couple times or something and see if it works out, but you can use this series as well. 5, use series to evaluate. Limit x goes to 0, e to the x minus 1 squared over x times sine x. So we've got limit x goes to 0, e to the x minus 1 squared over x times sine x. And I'm going to use the same approach. Here, this one, because I have that square, is probably going to be a little more difficult. E to the x minus 1 squared, that's 1 plus x squared over 2 plus some stuff times 1 plus x squared over 2 plus some more stuff. X sine x is x minus x cubed over 3 factorial is 6 plus x to the 5th over 5 factorial is 120 plus some more stuff. Limit x goes to 0. I'm going to worry about the bottom first. I'm going to get an x squared minus x to the 4th over 6. Oh, no, I made a mistake here. So what I was going to know here, let's just write this out and then correct the mistake. X to the 6th over 120. Probably you saw this already. This is just e to the x. I need e to the x minus 1 here on top. Right now I was going to say I'd get a constant term on top and then a 0 on the bottom. That would go to infinity, which is a legitimate limit, but it's not really the kind of thing I expect to happen. What I forgot here is I didn't do my minus 1 here. So I'm going to have to change my numerator. Let's get rid of all of this. So I'm going to get, let's do this in square brackets, 1 plus x squared over 2 plus some stuff minus 1 times 1 plus x squared over 2 plus some stuff minus 1. Here, so I subtract the 1's, and then what I end up with is x plus x squared over 2 plus some stuff times x plus x squared over 2 plus some stuff. Here. And then what I get, is x goes to 0. Okay, what I really care about is what the x squared term is on top. Any higher degree terms, the x squared on the bottom is going to dominate. So I only care about the x squared. Well, it's just x times x. So I'm going to get x squared plus blah, blah, blah on top. I could figure out an x cubed term if I wanted to, but it doesn't even really matter. So the 4th over 6 plus x to the 6th over 120 plus some stuff. This is going to go to 1 over 1. That's 1. So square is a little bit tricky, but I only needed one term, so it's not really that big a deal. All right, something different. Okay, this is a two-part question here. Part A is getting us ready for Part B. So Part A, we're going to use substitution to find the first 6 terms of the Taylor series for e to the negative x squared at x equals 0. So earlier, whoops. So what we're going to do is we're going to look at e to the negative x squared. Well, that's a sum, n equals 0 to infinity. So the series for just e to the x would be x to the n. So I'm just going to do a negative x squared to the n over n factorial. So if you replace that red negative x squared with x, you'll get the Taylor series centered at 0 for e to the x here. Well, that's going to make the series for e to the negative x squared, this thing I wrote down here. So what that is n equals 0 to infinity. This is a negative 1 to the n, x to the 2n over n factorial. And I think it wanted the first 6 terms. First 6 terms, so we get a 0, that's going to give us a 1. Plug in an n equals 1, I'm going to get an x squared. Plug in an n equals 2, I'm going to get an x to the 4th over 2 factorial. Plug in x equals 6, plug in n equals 3, get an x to the 6th over 3 factorial 6, 1, 2, 3, 4. Plug in an n equals 4, I get x to the 8th over 5 factorial is 24. And then n equals 5 gives me an x to the 10th over 5 factorial is 120, and then there's some more stuff. So this is 1, 2, 3, 4, 5, 6 non-zero terms here. Okay, so that's in some sense your answer. It's really the first 6 terms here of this series, first 6 non-zero terms. And then what we're going to do is I'm going to really use the previous series to find the first 6 terms of the power series for the antiderivative of e to the negative x squared dx. So note, there's no nice way to find an antiderivative of e to the negative x squared, but we can find a power series for it. So what I'm going to get is an antiderivative of e to the negative x squared dx. Well, how am I going to do that? I don't know how to, you could try and do some substitution here. It's just not going to work there. But if you have a power series for e to the negative x squared, you can just integrate these terms term by term. So I do an antiderivative of 1, that's x. Antiderivative of x squared, that's x cubed over 3. Antiderivative of x to the 4th over 2, it's going to be an x to the 5th over 2 times 5, that's 10. Minus antiderivative of x to the 6th is x to the 7th over 7. 6 times 7 gives me a 42. Antiderivative of x to the 8th gives me x to the 9th. See, 9 times 24 is going to be 216. 240 minus 24. And then I get an x to the 11th over 11 times 12 will be a 1320. So that's 1, 2, 3, 4, 5, 6. And, now it's not really an equals here. I suppose this is an approximately equal this. You could write a plus c here if you want, although I'm going to ignore that for now. So I just found an antiderivative here. So essentially we're just integrating a polynomial, which is easy. It's kind of an ugly polynomial. Oh, and sorry, this was actually 3-part here. So part C, now I'm going to use the previous answer to try and estimate the definite integral here. So going from 0 to 1 of e to the negative x squared dx. And I want my error to be at most 0.01. So what I'm going to get here is the antiderivative of 0 to 1, e to the negative x squared dx. Well, I should be able to plug in 1 up here minus 0. So essentially what I really need is my series here. And I'm going to find my series when I plug in x equals 1 minus when I plug in x equals 0. So let's plug in 1. N equals 0 to infinity, negative 1 to the n, 1 to the 2n over n factorial, minus n equals 0 to infinity, negative 1 to the n, 0 to the 2n over n factorial. So a little twist here. This first one, oh no, sorry, that's not our series. Here, this is the original series. That's without taking the antiderivative. So that's not what I want at all here. So let's get rid of this. Well, it's close to what I want, but that's not what I want. So what I want really is my antiderivative here. Let's just do the antiderivative evaluated at 1 minus the antiderivative evaluated at 0. Let's do it that way. So when I plug in a 1 here, what I'm going to get is 1 minus 1 cubed, which is 1, over 3, plus 1/10 minus 1 over 42, plus 1 over 216, minus 1 over 1320. When you plug in 0, you're going to get 0 here for each term. So you get this, and you could get more and more terms here, but no, this is an alternating series. And so our alternating series estimation says that the error from using sort of the first however many terms we have is at most the next term. So we want an error that's at most 1/1000th. So basically we just need this last term we don't use to be less than 1/1000th. So actually you could stop at 1 over 216. You could add up these first 5 things, and that would give you sort of something within 0.001. So let's just do this here. Let's do 1 minus 1/3 plus 1/10 minus 1/42 plus 1 over 216. And I'm going to add in the next term as well here. Give me even better approximation. So what I get is it's about 0.7467. 0.7467. That looks like my answer. Now, if it were me here, I would probably check this quick. So I can go on my calculator, math. There's a numeric integration. I can do e to the negative x squared, comma x, and I'm going from 0 to 1. So the idea is if I did this right, I should get something close to that. And there you see 0.746824, so we can get the point, let's see, if you subtracted these here, 0.7468241328 minus the 0.7467291967, you get an answer that's something times 10 to the negative 5th. We just wanted something less than 1/1000th, and that will satisfy that. So we did, assuming the calculator approximation is correct, or at least close, we did get really the answer we were looking for. Next one. I should note here, we did this kind of thing approximating integrals before, but we had to use like trapezoid rule or Simpson's rule or something like that. Here we just used the Taylor series. Worked out probably a little bit easier. All right. Now we're going to deal with binomial series. So binomial series, a little bit different here. What the formula is that if, a version of the formula, that if I do 1 plus x to the n, what I get is a sum. I'm going to do a k equals 0 to infinity, and choose k, and then you'll get an x to the k. So this is one version of the binomial series formula here. You'll see more complicated versions as well here. Now, what you probably saw, if you saw this in a previous course here, is not going k equals 0 to infinity, but k going 0 to n here. And that's going to be actually equivalent here. And the issue is, how do we define this binomial coefficient n over k? So probably what you saw, maybe you use Pascal's triangle to calculate these, but you might have seen something like n factorial over k factorial times n minus k factorial. Now, that definition's not going to quite work for us, because if k gets bigger than n, we have a negative number we're taking a factorial of, and that's not defined. So that isn't really what we want to do. Now, this is one definition that works. but not quite what we want to do. What you're going to do instead is take the n factorial, right? That is n times n minus 1 times n minus 2. Eventually, you're going to get down to an n minus k plus 1, and then an n, and then an n minus k, and then an n minus k minus 1, and keep going with those, and eventually 3 times 2 times 1. So you'll get that. I'm just doing n down to 1. I'm putting this n minus k business in here to cancel something out. And then what we're going to have is a k factorial. Let's see, so k factorial is k times k minus 1 here times k minus 2. Actually, I'm just going to leave that as k factorial for now as we go along, because the k is going to go positive. We can evaluate k factorial. And then n minus k factorial is n minus k times n minus k minus 1. And I keep going down until I get to 3 times 2 times 1. Well, what you notice here, if you look at this, is this last part of the n factorial matches my n minus k factorial, and so those will cancel out. And so we can do a new definition of this binomial coefficient, this n choose k, which is sort of, so it's consistent with our previous definition. We're just going to let this be n times n minus 1 times n minus 2, and then we're going to do n minus, and the last thing we're going to subtract is really k, and then we're going to do a plus 1. So not quite down to n minus k, but one bigger than that over k factorial. You'll note there's k factors on top here. So that's the way we're going to do it. And that allows us to do two things here. One is it allows us to plug in k's that are bigger than 0. Oh, no, that doesn't. No, sorry. It allows us to plug in k's that are bigger than n. That's what we want. Well, it does allow us k's bigger than 0, but not negative k's. K is bigger than n. It allows us to do that here. When you do that, if you do k is bigger than n, so let's do, how about 2 choose 3, what you get is you start with 2 on top, and you're going to go down until you get 3 factors on the top. Let's do something more interesting. How about 2 choose 5? So now we'll want 5 factors on top of bottom. So you get 2 times 1 times 0, that's 3, times negative 1 times negative 2, over 5 factorial is 5 times 4 times 3 times 2 times 1. 5 factors on top, 5 factors on the bottom. On the bottom, you start at 5. On the top, you start at 2. Essentially, that's all you do. Now, what you'll notice here is that I have a factor of 0 on the top. So if I start at a whole number and I subtract more than that whole number, I'm always going to get 0 on the top over something. Works out to be 120 here. Doesn't really matter what it is. That gives us 0. And so if the bottom, our k, is bigger than n, we're always going to get 0. And that's why in this series you could have stopped at n instead of going to infinity, because this coefficient's always 0 if k is bigger than n. So completely consistent with what you might have seen before. So that's one thing. The other thing that these definitions are going to do is this n, I can make that a fraction or a negative number. So I could do, say, negative 4 choose 2. Well, then our definition is you take negative 4, you subtract 1, note that's negative 5, 2 times 1, there's temptation to write negative 3 there, and that gives me 20 over 2, that equals 10. So you can use negatives in there. Doesn't have the same meanings as before, but you can calculate this way. You could also do like 1/3, choose 4. So you can put a fraction in there. This would be 1/3. Next one, subtract 1 from 1/3, you get negative 2/3. Subtract 1 again, you get negative 5/3. Subtract 1 again, you get negative 8/3. All over 4 times 3 times 2 times 1. Should be 4 factors on top, 4 on the bottom. And then you just have to simplify this down. So I've got 3 negatives, so I'll get a negative answer. Let's see, I'll get 2 times 8. Well, let's see, the 4 and the 2 will cancel with the 8. So I'm going to get a 10. And I've got a 3 on the bottom, and 1, 2, 3, 4 3s down there. I think that's going to be negative 10, 240 thirds. So you have a new way to calculate these. Okay, and then what that does, essentially, is allows us to find power series for new things using sort of a binomial series formula. So let's look at one of these. 1 minus x to the 9th. Okay, 1 minus x to the 9th. Now, again, what we're going to have to do is recognize this as 1 plus negative x to the 9th. And then using our binomial series formula, this is going to be k equals 0 to infinity. N is 9, choose k, times x, well, the thing we're plugging in for x, that's a negative x to the k. Let's look at our directions. Find the first 4 terms. So we're going to plug in k equals 0. You get 9, just do 9, choose 0, times negative x to the 0 is 1. And then we'll get plus 9, choose 1, negative x, plus 9, choose 2, negative x squared, 1, 2, 3, one more term, 9, choose 3, negative x cubed. Okay, 9, choose 0, that's going to end up being a 1. 9, choose 1, that will be a 9. Here, so anytime I do a choose 0, that's 1. Anytime I do a choose 1, that's the top here. Plus 9, choose 2, I do 9 times 8 over 2 times 1, x squared. The cubes, I'm going to get a negative. I'm going to get 9 times 8 times 7 over 3 times 2 times 1, get x cubed. So I get 1 minus, oh sorry, I left my x off here in this second term. 1 minus 9x. Let's see, 2 and 8 cancel for 4. So that's plus 36x squared. 3 will cancel with the 9. 2 will cancel with the 8 for 4. So I get 12 times 7 is 84. So minus 84x cubed. So there's my first 4 terms of a series for 1 minus x to the 9th here, centered at 0. Okay, and that one, I mean, you could find an actual polynomial. That series, eventually the coefficient is going to be 0 when k gets bigger than 9. It's only going to go up to x to the 9th here. That's kind of a warm-up question. Next one, we do something more interesting. We make this exponent negative 2. So we do 1 plus x over 3 to the negative 2. Using our binomial series formula, this is k equals 0 to infinity. It's n, that's negative 2, choose k, times x, which is, well, the thing we're doing 1 plus x over 3 to the k. So I'm going to do k equals 0. That's, whoops, negative 2, choose 0, plus k is 1, negative 2, choose 1, times x over 3, plus k is 2, negative 2, choose 2, x over 3 squared, plus k is 3, negative 2, choose 3, x over 3 cubed, and then plus some stuff. Okay, so if I choose 0, that's 1. Negative 2, choose 1, I get a negative 2 over 1 here. So 1 factor on top and bottom times x over 3. Next one, I'm going to get a negative 2. Subtract 1 from negative 2, that's negative 3. 2 times 1. 2 factors on top and bottom times x squared. 3 squared is 9. And then the last one, I'm going to get a negative 2 times a negative 3 times a negative 4. I need 3 factors. 3 times 2 times 1. And I get an x cubed over 27. So what I get is 1 minus 2/3 x. So 2 times 3 is, well, 6. Well, negative, negative is positive. I can cancel 2's. I get a 3, cancels with the 9. Here I'll get a 3, so this is going to be plus 1/3 x squared. Next one is going to be a negative. I can cancel a 2, I can cancel a 3, so I'm going to get minus 4/27 x cubed. So there's really my first 4 terms of my series for 1 plus x over 3 to the negative 2. Here. Let's see, another one. 1 minus x to the 1/3. So here's one with a fractional exponent. So what you get is a sum n, not, well, could use n here, I guess. I'm going to use k, 0 to infinity. N is now 1/3. Choose k. And I get an x, not an x, really it's a plus negative x. So I get a negative x to the k. K equals 0, gives me 1/3, choose 0. K equals 1, gives me 1/3, choose 1, times x, times negative x. K equals 2 gives me 1/3, choose 2, times negative x squared. k equals 3 gives me 1/3 choose 3 times negative x cubed. Okay, so we get a choose 0, that's 1. We get a 1/3 choose 1, that's just 1/3, so it's a minus 1/3 x. And then with the 2's, I get a 1/3 times 1/3 minus 1, that's a negative 2/3, over 2 times 1. 2 factors on top, 2 factors on the bottom. Negative x squared is x squared. With the sort of 1/3 choose 3, I get a 1/3 times a negative 2/3. Subtract 1 again, you get a negative 5/3 over 3 times 2 times 1. And then I'll get that times a negative x cubed plus some stuff. So I end up with 1 minus 1/3 x. See, the x squareds I can cancel with 2. I have a negative, so it's going to be minus 1/9 x squared. The x cubes I can, let's see, I've got a 3 on the bottom. 2 and 2 will cancel. I have 1, 2, 3 negatives. So that's a negative. Let's say I've got a 5 over 1, 2, 3, 4 3's multiplied together. That's 81st. So if I did this correct, you get 1 minus 1/3 x minus 1/9 x squared minus 5 81st x cubed. So a little different, but something you can still kind of work out. The last one here. I'm going to do one more thing here with our power series, is you can estimate values like cosine of 0.1 here. So what's going to happen here is we're going to say this 1 minus x squared over 2 plus x to the 4th over 24. That's the first 3 terms here of the, essentially the 4th degree, first 3 non-zero terms of the Taylor series for cosine x. So cosine x is approximately 1 minus x squared over 2 plus x to the 4th over 24. And there's a question here, essentially, of how big is the error here. So there's a power series estimation theorem here that says if I go up to order 4, note this is also the order 5, because the coefficient at 5 is 0, so I can either do 4 or 5. What I get here is that the error here, so our error is really, so it's going to be, say, cosine 0.1 minus 1 minus 0.1 squared over 2 plus 0.1 to the 4th over 24 squared. So I take an absolute value of that, so I'm subtracting this here. That error, that's our error. So it says the error is bounded above by essentially the next term in the Taylor series, but it would be an n plus first derivative. So in our case, it would be a 5th derivative, or a 6th if you think about this as 0x to the 5th. So we're going to do a 5th derivative. So it's going to be a 5th derivative of f. But what you're going to do here is really evaluate that at that 0.1 here. And then you divide by the 5 factorial here. So it's evaluated at 0, you would actually get the next term, but we have to evaluate it at 0.1. So to do this, well, it's really bounded by the absolute value. So what we need to do is take the 5th derivative, sorry, it's not really 0.1, it's the maximum value. Let's put it here. Let's put in how about an A, but a C maybe is more common, of C for some C with in our interval from 0 to 0.1, and let's just fill that in there with close brackets. So I can do, here I want the maximum value, actually really for all of C here. So I want the maximum value there. So let's find the 5th derivative. So f of x is cosine x. F prime of x is negative sine x. F double prime of x is negative cosine x. F triple prime of x, derivative of negative cosine x, is going to be positive sine x. The 4th derivative of x is going to be then cosine x. And the 5th derivative of x will be a negative sine x. So we get a negative sine x here. And we want to maximize negative sine x in the interval 0 to 0.1. Well, if you graph sine x, you'll get a graph that looks like this kind of a thing. So it's going to be maximized at 0.1. So our error, here your error then is at most, it should be sine, really negative sine of 0.1 over 5 factorial. We'll bound this above here. And to calculate that, I'm going to go to my calculator. So sine of 0.1, don't really need the negative because I'm taking an absolute value, divided by 5 factorial is 120. Tells me this error is at most, 0.000 is 8.3, we'll say. 3.2 if you round that. So that tells me the error there. Let's check and see what the error actually was here. So we can do, let's see, what were we trying to do? We were trying to evaluate cosine of 0.1. So let's see, cosine of 0.1 minus 1 minus 0.1 over squared over 2 plus 0.1 to the 4th over 4. Let's see what the error was. I really want an absolute value of that. So we do a cosine of 0.1. Let me subtract the 1. It should be the negative. It's plus 0.1 squared divided by 2 minus 0.1 to the 4th divided by 24. That gives us an error. Note our actual error is something times 10 to the negative 9th here. So our actual error is 0.1, 2, 3, 4, 5, 6, 7, 8, and then we had a 1, maybe 3, 9. Actual error is much, much smaller. So we said we got an error of at most 0.000832. Actual error is a lot smaller here. One thing I'll point out about this question here, is I mentioned this a couple times, is that actually this Taylor series, this is plus like 0 x to the 5th. So it's really an order 5 Taylor polynomial. So you can, generally this will be a better bound here, take the 6th derivative. Maybe I'll do this in red here. Talk about this. So either one of these would be fine here as an answer. 6th derivative, let's see, would be a cosine x. And so then it tells me my error is at most cosine. Okay, now we got to think about this. Cosine x from 0 to 0.1, the graph of cosine x starts at 1 and goes down. So I really want a cosine of 0 is where it's maximized. That's at 1. So it should be 1 over 6 factorial. That's 1 over 720. That's not really helping us a lot here. So that error, if we go there, actually isn't as good. So we probably want the error we had already here, 0.001, but the one we had already is much better. And that's going to end our problems for this video.